This section of the book is on using calculus, limits, and derivatives to draw graphs of functions. And in theory, if we could draw the graphs of functions perfectly well, we'd be able to answer lots of other questions. Of course, this section isn't as important as it used to be. Graphing calculators and computer programs have gotten so good at graphing, and they're so fast, and they're so common that graphing by hand isn't as important a skill as it used to be. But still, when you have a calculator graph a function for you, or a computer graph a function for you, you typically have to give it a window in which to graph. So you tell it, oh, my x-coordinate's between here and here, and my y-coordinate is between here and here. It doesn't know, your calculator or computer doesn't know ahead of time where the interesting features of the graph are. And it's possible that you can't even see all the interesting features in the same window with the same scale. And so what we can do by hand, though, is find all the interesting activity on the graph, find all the interesting places, and either graph them separately or have at least graph them separately by hand, or we find the right windows and the right scale and then we give it to a calculator or computer. Or by hand we can also just kind of arbitrarily fudge our scales in different parts of the graph to show the interesting activity in places, even if we're using different scales on different portions of the axes. So graphing is still important, and it reinforces so many of the calculus techniques that this section is worth doing. We're going to do a couple of fairly easy examples, and then I'll start a complicated one. I'm not convinced that I want to take the time to finish all the details of it. Certainly it's in the book. So when you're graphing, when you're drawing the graph of a function by hand, there are at least 6 separate things that you should consider. So first, of course, you want to know the domain of your function, the allowable x's. And you'd kind of like to know the range, but it's impossible to know the range ahead of time, or almost impossible to know the range ahead of time. It's too complicated for most functions. But you certainly would like to know the domain. After that, there's kind of the first calculus thing you'd like to know. So what the first derivative tells you. Well, we know that where the first derivative is positive, the function is increasing, so the graph goes roughly from the lower left to the upper right, so it has positive slope. When f prime is negative, the function is decreasing, the graph roughly goes from the upper left to the lower right, so it has negative slope. And where the function changes from increasing to decreasing, or decreasing to increasing, we have these local extrema, local maxima and minima. So this is the second thing. The big word, it's a cool word, now let's see if I can spell it, monotonicity. Monotonicity and extrema. So monotone, that's where it's increasing, where it's decreasing, and extrema, the local maxima and minima. We want to find those, and this uses, here you look at f prime to do these. 3, we want to look at the concavity, where the graph is concave up and where it's concave down, and the points where it switches from concave up to concave down. So those are the points of inflection, or the inflection points. And this, of course, uses f double prime, the second derivative of f. Look at f prime. Look at f double prime. All right. The fourth thing in my list that we want to look at involves limits, but not derivatives. We want to look at asymptotes. And activity at infinity. So this means we'd like to look at the limit as x goes to infinity of f of x. So we'd like to know what this does. So as x gets really big, what does f of x do? Because we want to know that we indicate on our graph somehow what the function's doing, even on the parts of the graph we can't draw. As x gets really big, well, we can't keep drawing x arbitrarily far out. So we'd like to know that we've given some indication on the graph of what does happen as x gets big. And then we need negatively big, I mean, big in absolute value, but negative. So as x approaches negative infinity, we'd like to know what happens. If f of x approaches a number, a finite number, like 2 or something in one of these cases, then that's called, you have a horizontal asymptote. You should have looked at these in high school. We also want to know places that x can approach where f of x approaches plus or minus infinity. So here we're letting x go to plus or minus infinity. We want to know what the value of f of x does. Here we're letting x approach a either from the left or from the right, really from the left or from the right. And we'd like to know if f of x goes shooting off to infinity as x approaches some value. Where this happens, those are called vertical asymptotes. We'll see this in an example. And for continuous functions, you would necessarily have to have f of x undefined at a for this kind of thing to happen, because continuous means continuous at each point in your domain. To go shooting off to infinity at a point, well, infinity is not a number. A wouldn't be in the domain of this function if f is continuous at a, and a is plus or minus, and this limit is plus or minus infinity. The fifth thing we'd like to look at is symmetry. This is even in oddness. Even functions. F is even, and this again is something you should have seen. A function is even if its value at negative x is always the same as its value at x. And if x is in the domain, negative x is in the domain. That's an even function. An odd function, when you put in, actually let me write this the other way, just so it'll look like what I'm about to write. For an odd function, f of negative x, you get negative the value of f of x. This is an odd function. What effect do these have graphically? Well, for an even function, this is an example of an even function. So something like, let me draw a parabola. It's an even function, or the graph of an even function, which means the y-coordinate at a given x value, so here's some x value, well, here's the corresponding negative x, and you're supposed to have the same y value. So that means that if you have a point over here where x is positive, if you have a point on the graph and you go pass through the y-axis and go out the same distance along this horizontal line to the other side of the y-axis, that corresponding point should be a point on the graph. The one that's negative x, it should have the same y-coordinate. This means that your graph, if you flip it around the y-axis, you get the same thing. This is, people say this is even. This is, the graph is symmetric about the y-axis. And if your graph is symmetric about the y-axis, then you only need to graph your function for positive x's, and then you can just flip it around the y-axis to find what happens for negative x's. For that reason, you could check symmetry first, so that you know you only have to do half as much work. In fact, I probably won't do that, because it just seems more natural to check where the first and second derivatives are positive and negative everywhere instead of artificially just looking at the positive x's and then flipping. But we will note that symmetry could have saved us some work. And then odd functions. For an odd function, for an odd function, it's that if, so what does this say? This says if you, suppose I have a point, here's x, here's f of x. So here's x, f of x. If the function is odd, it means when I negate the x coordinates, when I go over here the same amount, I am supposed to get negative this f of x coordinate. So when I negate the x coordinate, I negate the y coordinate, which means if I've got a point like AB, or x, f of x, over here I get negative x, negative f of x. But that's the point that you get if you take a line through the origin and go the same distance along that line out the other side into negative territory that you got over here. So just like evenness corresponds to symmetry around the y-axis, this is symmetric about the origin. And that means, again, that if you just graph the function for positive x's, it's enough, because then you can just grab the graph. Actually, if you could just stick a pin in right there and rotate it around 180 degrees, so pi radians, 180 degrees around the origin, the graph would look the same. So again, you only have to draw half the graph and then kind of use the symmetry about the origin. The last thing, number 6, that can be helpful for graphing, although it's pretty easy, is just indicate some special points. So I mean, besides maxima and minima, besides inflection points, indicate other special points. Like what? Plug in some x and y values, but typical ones, ones that people like, the x and y intercepts. So where the graph hits the x and y axes, if it does. All right, those are the 6 things we want to worry about when graphing. If you look at all of those, you can draw very accurate graphs. So let's do 2 fairly easy examples and then at least start a hard one. So let's look at x squared over x squared minus 1. All right. The domain of this function. Well, we just don't want to divide by 0. So the domain all x unequal to, we don't want x squared minus 1 to be 0. When is x squared minus 1 equal to 0? When x squared is 1, when x is plus or minus 1. So we don't want x to be plus or minus 1. Okay. All right, let's look at the derivatives. There is one nice thing you can do algebraically here. You don't have to do this, but it does make things a little easier. There's an x squared in the numerator and 1 in the denominator. You could long divide the denominator into the numerator, but the long division isn't very long and just amounts to adding 0 in a clever way. What's a clever way? Well, this way. Subtract 1 from the numerator, but then add 1. So we haven't changed the numerator. How is this useful? Well, if you group it like this, then you can split up this fraction as x squared minus 1 over x squared minus 1. That's 1 plus 1 over x squared minus 1. Why do this? Because it makes the derivative significantly easier to calculate, for one thing, because we can write the function like that. All right. So if we do that, or even if we don't, if we didn't do that, we could use the quotient rule. If you have done this, if you rewrite it that way, what you find is we want to look at monotonicity. We want to look at where the graph is concave up, is where the function is increasing, where it's decreasing, and consequently find also local extrema. So we calculate that y prime is, now it's easy to differentiate this. The derivative of this part is 0, the derivative of this part, use the chain rule, you get negative x squared minus 1 to the minus 2. So, but then times the derivative of the inside stuff, so times the 2x. So you get negative 2x divided by x squared minus 1 squared. And what we'd like to know is where is this positive and where is it negative? And where can it switch signs? So what we usually do is find out where it could possibly switch signs and check in between there on the intervals in between those places and see whether it's positive or negative. This denominator is squared. It's always greater than or equal to 0, and in fact we're not looking at where it equals 0 because that's not in the domain. So this denominator is always positive. So y prime being positive or negative is completely determined by where the numerator is positive or negative. There's a minus sign. So what's true is when x is negative, when x is less than 0, y prime is positive. When x is greater than 0, y prime is negative. But I should say x less than 0 and unequal to minus 1, because that's not in our domain. And when x is greater than 0 and x is unequal to 1, y prime is less than 0. You can, of course, do this with a number line. You can say, all right, let's look at the sign of, let's look at where f prime is positive and where it's negative. Where can it switch signs? This is a continuous function. It could switch signs, if we're writing the whole number line, it could switch signs where this is undefined or where it hits 0. It's undefined at minus 1, at plus 1, and it is 0 at 0. So here it's 0, there and there it's undefined. Those are the only places it could possibly switch signs, and then you can just check the sign in between. Now we know what we're going to find because this is an easy function, we could tell, but you could just plug in any number between 0 and 1 to see whether the derivative, whether f prime is positive or negative in here. Between 0 and 1, though, this is positive, this is negative, so you get negative in this region. I'm indicating a minus sign. When x is greater than 1, this is positive, this is negative, so you get negative, and you get positive and positive over here. So, okay. So that's what the first derivative does. In fact, it would be helpful to record that somewhere out of the way. Where will we see extrema? Well, to see local extrema, you need a point in the domain of the original function where so local extrema, you'd need to see a place where the first derivative is positive on one side and negative on the other, or vice versa, and a place that's defined, where the original function is defined, at 0. At 0, we increase until 0, and we decrease after that. So we should see a global maximum occurring. Well, I don't know why I said a global maximum. We should see a local maximum occurring at 0. There's No reason why it has to be global, since, yes, if the function increased all the way until here and then decreased all the way over here, we would have to have a global maximum occurring at 0. But we have these places where the first derivative is undefined. And so all we really know is that there's a local maximum occurring at x equals 0. We don't know that it's global. All right, but let me put this number line for f prime up here, more or less out of the way, so that we can have it for later. So we have minus 0 here, plus, and it's undefined here and here. Okay. And that also lets us know where local extrema occur, because we see where the function switches from increasing to decreasing. All right, we need f double prime. So we want to look at concavity and inflection points. Inflection points are where the second derivative changes signs. All right, so our first derivative, graphing problems take up a lot of space, and you have to learn to get things out of the way. So we've got this for y, what we found for y prime. For y prime, we found minus 2x over x squared minus 1 squared. We need y double prime. We will use the quotient rule. We'll pull out the minus 2, but after that, we'll use the quotient rule. So we need y double prime. So we're now worried about concavity. So the third thing we had said we needed to worry about, concavity. So we want to look at the second derivative. So I'm going to pull out this minus 2. You get minus 2 times. And then we need the quotient rule. It's the bottom, so the x squared minus 1 squared, times the derivative of the top, except I've pulled the minus 2 out. So let me write it as. So the bottom times the derivative of the top. The derivative of x is just 1, minus the top, the x, times the derivative of the bottom, 2. X squared minus 1 to the 1, but by the chain rule you have to multiply it times an extra 2x, all divided by that denominator squared. So x squared minus 1 squared squared, so to the 4th. This, yuck, yuck, this is horrible. We need to simplify this because we want to be able to tell where it's positive and where it's negative. One thing you can do is there's an x squared minus 1 here, there's an x squared minus 1 there, and an x squared minus 1 there. So we can certainly divide away 1 power of x squared minus 1. So I'll just make that a 2. This part's gone. Make this a 3. So we get this. Well, that actually did get a lot nicer. This is minus 2 times. All right, we get x squared minus 1. And then minus 2x times 2x, so minus 4x squared over x squared minus 1 cubed. This is minus 2 times, we get a minus 3x squared, a minus 3x squared minus 1 over x squared minus 1 cubed. We can pull out a minus sign here and write that this is 2 times. So pull out a minus sign, it cancels that one. 3x squared plus 1 over x squared minus 1 cubed. What we want to know is where this is positive and where it's negative. But the numerator, 2 is always positive, 3x squared plus 1 is always positive. It's completely the denominator that's determining where this is positive and where it's negative. This function will be negative where x squared, and this is cubed. So something cubed. You cube a negative number, you get a negative number. You cube a positive number, you get a positive number. So where x squared minus 1 is positive, this will be positive. Where x squared minus 1 is negative, this will be negative. Where do those things occur? Well, you can check. But again, the only place you can do the number line, where you can get it from what I just said, but the only place that you can switch signs are 1 and minus 1, and we have y double prime is 2 times 3x squared plus 1 over x squared minus 1 cubed. All right, so this doesn't equal 0 anywhere. The only place it's undefined, plus at minus 1. What is it in between plus and minus 1? Positive or negative? Put in x equals 0. This is positive, positive. You get minus 1 cubed. So that's minus 1. So it's negative in here. When x is greater than 1, positive, positive, this will be positive. When x is less than minus 1, like minus 2, this will still be positive. So you get plus here and plus here. So we see the concavity is positive when you're at when x is less than minus 1, and negative when x is greater than minus 1, for a little while anyway. Do we have a point of inflection occurring when x equals minus 1? No, x equals minus 1 is not in the domain of our function. So the only places where we could see points of inflection are minus 1 and 1, but those aren't in the domain of our function. So the graph will have no points of inflection. No places where we see the concavity switch from positive to negative or negative to positive at a particular point on the graph. It could happen at an asymptote, but it doesn't happen on the asymptote. All right, which brings us to asymptotes. So we want to know about asymptotes of the original function. So there are two kinds that we worry about, horizontal ones and vertical ones. The horizontal ones tell you what happens as x goes to infinity. We'd be interested in that even if there's no asymptote, even if there's no particular number that you approach. So we go back to our original function, f of x. So f of x is x squared over x squared minus 1, which we also wrote as 1 plus 1 over x squared minus 1. All right. What is the limit as x approaches infinity of f of x? Oh, as x goes to infinity, this denominator goes to infinity. 1 over that, 1 over infinity, that goes to 0, and we're left with 1. So this means y equals 1 is a horizontal asymptote. As x approaches minus infinity, same thing happens. As x approaches negative infinity gets squared, so that's infinity, 1 over infinity, 0. You get 1 again. So y equals 1 is a horizontal asymptote that the graph approaches both as x goes to infinity and as x goes to minus infinity. What about vertical asymptotes? Well, let me go ahead and start graphing this because it's a lot easier to talk about asymptotes with the graph in front of you. So what do we know so far? Well, let's just try to draw our graph, sort of. Here's minus 1, where the function is undefined. Here's 1, where the function is undefined. Here's 1, where we know that there's a horizontal asymptote that the graph approaches. Okay. Vertical asymptotes. Those are points, x-coordinates that you can approach and have the value of the function go off to infinity. So we're looking at this function. So 1 plus 1 over x squared minus 1. And we want to know what values x has to approach from the left or from the right to make this go to infinity. Well, all the functions, all of our elementary functions are continuous everywhere they're defined. For a graph to go off to infinity, it would, and if the function is continuous, well, then the function is going to have to be undefined there, because the limit as you approach is supposed to be the value of the function there, but the limit's infinite, so the value of the function would have to be infinite. That's not defined. We'd have to have our function be undefined. That means the only possible places that we can have vertical asymptotes are at minus 1 and 1. That does not imply that we have them. We have to check that as we approach 1 and minus 1, the function actually goes off to positive or negative infinity. But we'll see that. So what happens as x approaches, let's look at 1 from the right. As x approaches 1 from the right. So that means through x value slightly greater than 1. If x is slightly greater than 1, x squared slightly greater than 1, this is slightly greater than 0. But as you approach 1, it gets closer and closer to 0, but through values greater than 0. So it's like a positive 0, 0 from the positive side, which means 1 over it gets huge and positive. Plus 1, huge and positive, in the limit, positive infinity. So what that says is, as x approaches 1 from the right, through numbers slightly greater than 1, the value of your y-coordinate is going off to infinity. So yes, we have a vertical asymptote at 1, and the graph has to go off to infinity, positive infinity, as x approaches 1 from the right. What happens as x approaches 1 from the left? As x approaches 1 from the left, x is slightly less than 1. Something slightly less than 1 squared is slightly less than 1. This would be close to 0, but negative. So 1 over it is something huge in absolute value, but negative. In the limit, you get negative infinity. And so what has to be happening is, as x approaches 1 from the left, we go off to negative infinity. We do that. I'm not going to draw what happens over here. I am going to use symmetry and just flip things around. So we'll see. We'll see what happens. All right, but that's the asymptotes. The horizontal asymptotes, we found that as x approaches infinity, we approach 1. As x approaches minus infinity, we approach 1. So we could be doing something like this or this. We don't really know right now whether we approach 1 from numbers bigger than 1 or through numbers less than 1. For that matter, we don't really know that we don't do something bizarre like oscillate back and forth and approach 1. I mean, there's no reason you can cross horizontal asymptotes. So we don't really believe it would oscillate back and forth without some trig function in there, but right now we don't know that it can't. All right. So that's asymptotes. We'd like to look at even and oddness. In fact, this function is even. And it's not a coincidence that you see only even powers of x in here, including a constant, which is like times x to the 0. If you look at f of negative x, so you replace that x by the quantity negative x, it means you replace this x by the quantity negative x, and that x by the quantity negative x. And you square. But because you've squared, this is just x squared, this is just x squared. And of course, this is the same as f of x. What this means is that the graph is symmetric about the y-axis. So symmetric about the y-axis. So if we sketch the graph for positive x, we flip it around the y-axis to see what we get for negative x. Symmetric about the y-axis. Finally, I said it's good to look at special points. What's one special point? So the x and y intercepts. So when x is 0, y is 0. So when x is 0, that's the y-intercept. So the y-intercept is 0. The x-intercepts, where you hit the x-axis, where y is 0, well, that's also 0. So there's only one intercept here. It's the x and the y-intercept. Aside from that, they don't hit the x and y-axis. Can we graph this now? Well, I sure hope so. So what happens? We see that when we have, let's look at between, I'm only going to do this for positive x's, and then we'll use symmetry to get the other half of the graph. So what did we see here? We saw that at least on the interval from -1 to 1, we should have a global maximum of 0, just restricted to that interval, because on that interval, f prime is positive and then negative. So that means f itself increases and then decreases. So the global maximum of the function, at least for for those x's in between -1 and 1, not a global maximum necessarily, is here. So, and then the function decreases the whole time. It decreases the whole time until 1. It's decreasing and concave down. Decreasing and concave down, it approaches negative infinity as an asymptote. So it does this. Decreasing, concave down. So decreasing roughly goes from the upper left to the lower right. Concave down, it's curved downward. It approaches this as an asymptote. Great. On the other side of this asymptote, what happens? The function has to still be decreasing, but now it has to be concave up, and it has to approach infinity as you approach 1 from the right, but it has to approach 1 as x approaches infinity. It has to do this. It has to be concave up, because this is positive. It has to be decreasing because of this. It has to go roughly from the upper left to the lower right. It has to approach infinity as you approach 1. It has to approach 1 as you approach infinity. It has to do this. Why can't it do something like go below here and then come back up to approach 1? Because the function is always decreasing. It can't do that. And also the concavity would, but it can't go below here and then go back up. So it can't ever go below there, because then it wouldn't approach this as an asymptote. And now by symmetry, you reflect this around the y-axis, and you get the other half of the graph. So and that's what the graph looks like. If you ask a calculator or a computer to do this, they can do this one pretty easily. You'll get a decent looking graph. Okay. As you can see, it takes a long time to look at all of this data. To graph things relatively accurately takes a lot of data, it takes a lot of time, it takes a lot of space. Probably the best combination these days is not to actually graph the function by hand, but to use calculus to tell you where the interesting points on the graph are, the interesting features, and then use that to tell you what windows to give and scales to give your calculators or computers. Although that may not be quite true. If you punch in something slightly wrong on a calculator, you could get a wildly incorrect graph, and it would be good to know vaguely at least vaguely what the graph looks like by doing it by hand. Of course, you could make a mistake doing any of the calculus and get a wildly incorrect graph too, so hard to say which is likely to be more accurate. Let's look at a different function. Let's look at y equals g of x equals x e to the minus x. All right, the domain, no problems with the domain here. Domain here, all real numbers. So the entire real number line, the entire interval from minus infinity to infinity. Fine. What about the first derivative? Y prime. We use the product rule and the chain rule. It's the first thing times the derivative of the second, but the derivative of e to the minus x, you get e to the minus x back, but times the minus 1. First thing times the derivative of the second, plus second thing times the derivative of the first. The derivative of x is just x. you get this. You can factor out the e to the minus x. This is e to the minus x times minus x plus 1. E to the minus x is always positive. So this function is positive or negative exactly where minus x plus 1 is positive or negative. So it's easy to draw the y prime number line and decide where y prime is positive and where it's negative. The only place it equals 0 is undefined is when x is 1. It's the only place it could switch signs. And when x is greater than 1, this is negative, so this whole thing is negative. When x is less than 1, and here it's 0. When x is less than 1, it's positive. So we do have a global maximum for this function occurring when x is 0. When x is 1. The value of the derivative is 0, but what's important is when x is 1, the function increases before that and always, and then decreases after that always. So yes, there's a global maximum of y occurring where x equals 1. What about y double prime? All right, we use the product rule again. It's the first thing times the derivative of the second. So the e to the minus x. First thing times the derivative of the second, plus the second thing, the minus x plus 1, times the derivative of the first thing, e to the minus x times another minus 1. Again, you factor out the e to the minus x, and you get, if you multiply this out, you get a plus x minus 1 minus another 1. So you get a plus x minus 2, positive x minus 2. So where is this positive and where is it negative? Well, you draw a y double prime number line. Only place it's undefined or 0 is at 2. Here's 2. When x is greater than 2, it's positive. So like 3, this is positive. When x is less than 2, it's negative. So yes, this graph will have a point of inflection at x equals 2. The graph is, the second derivative is negative before there, so concave down. And then it's concave up after that. All right. What about asymptotes? This function is continuous and not undefined anywhere, so there aren't any vertical asymptotes. But there could be horizontal asymptotes, and those you find by looking at where, looking at what happens when x goes to positive infinity and when x goes to negative infinity. So what's the limit as x approaches infinity of x times e to the minus x? All right. This, there are a number of ways you can look at this. One would be to get out a calculator and take a very large x. And take that very large, how large? Try 1,000 or 100 even. Take 100 divided by e to the 100. E to the 100 will be so much bigger that this will be very close to 0, and as x gets bigger and bigger, this approaches 0. Later, we'll have something called L'Hopital's rule that will tell us that this limit is 0. Right now, what you can do is we had as our definition of e to the x that it's a limit of things of the form 1 plus x squared over 2 factorial plus, and then e to the x was actually greater than any of these polynomials. We could keep going out, but it's greater than this one. But that means 1 over e to the x is positive, but it's less than 1 over 1 plus x squared over 2. So you could use this to see that this limit is 0, because if you multiply through by a positive x, you'd get that this is true. And if this limit goes to 0, then we could use the pinching theorem and conclude. So we could say that this is less than or equal to the limit as x approaches infinity of x over 1 plus x squared over 2. And then if you want, divide the numerator and denominator by x, and you get that this is 1 over, and then you get a 1 over x plus 1 plus x over 2. What's the big deal? The big deal is that The big deal is that I didn't want to divide by that. I changed infinity to a 0. That's one big deal. As x goes to infinity, 1 over x goes to 0. So then plus 1 plus something going to infinity. So you get a 0 plus 1 plus something going to infinity. Denominator goes to infinity, 1 over that, 0. One way or the other, you need to know that this limit is 0. So that means that we have a horizontal asymptote at y equals 0. On the other hand, as x approaches minus infinity, what happens? Then this is going to minus infinity. This exponent on the e is going to minus infinity. E to the infinity, that's infinite, times minus infinity. Minus infinity times infinity, minus infinity. So this limit is minus infinity. That doesn't mean there's an asymptote, but it's still important to note that as x goes to minus infinity, our function goes to minus infinity. You can check. This function is neither even nor odd. Special points, we want to know maybe the intercepts. When x is 0, y is 0, and the only time y is 0 is when x is 0. So again, there's only one intercept, x or y intercept, and it's at the origin. All right, we can graph this now. So what happens? We found, actually maybe I'll graph it over here. So what did we find? We found that where x is 1 and where x is 2 are interesting points. The intercept is another interesting point. So here's x is 0, here's x is 1, here's x is 2. What does the graph do? All right. The y prime is positive until 1 and negative after that. So y itself increases until x equals 1 and decreases after that. When x is 1, the value of the function is 1 times e to the minus 1. So it's 1 over e. I'm going to just pick my scale by hand the way I want to. I'm just going to say 1 over e is here. Right? And this is a global maximum. The function increases until 1, and the y-coordinate is 1 times e to the minus 1, so 1 over e. Our function increases until there and decreases after that. It's concave down until 2. So until 1, it's increasing and concave down. After 1, it's still concave down until 2, but it starts decreasing. So now it was concave down and increasing. Between 1 and 2, it is decreasing and still concave down. So it's decreasing and concave down. Does it go below the x-axis? Well, you can, if x is positive, this is positive, e to the minus x is always positive. So no, it doesn't go below the x-axis. So it's decreasing and concave down until there. At 2, you're at 2 e to the minus 2. So this is, here you're at this y-coordinate, this point, is 2 over e squared. And then what happens? After that, the function continues to decrease, but the graph is concave up. So decreasing, concave up, and as x approaches infinity, x e to the minus x approaches 0. So that means you approach y equals 0, the x-axis. And we saw that as x approaches minus infinity, x e to the minus x approaches minus infinity. So as x approaches minus infinity, your y-coordinate approaches minus infinity. Right. So that's what you get for the graph. I'll draw it bigger over here, but maybe it shouldn't. I would indicate 3 special points on this graph. The origin, 1, this point, 1 over e, and this point, where the inflection changes, which is supposed to be, our point of inflection, which is supposed to be 2 over e squared. And you can look at your calculator and see that this is, it can draw this fairly accurately. All right. Let's start one more graphing problem. I don't believe I'll finish this. It gets very ugly. The details are in the book. But just as an example of something that you can do by hand, not quickly, but you can do by hand, that a calculator has a lot of trouble with, especially if you don't know any good windows to use. A third example is e to the minus x times secant x. I remind you that secant is 1 over cosine, so this is e to the minus x times 1 over cosine. Of course, e to the minus x is 1 over e to the x, so this is 1 over e to the x times cosine of x. What's part of the problem here? I'm going to do this in not the order I listed things in. Part of the problem is this is undefined every place this denominator is 0. All right, so I guess this is in the order I talked about because I'm going to do the domain, but I was going to mention asymptotes at the same time. The domain of this, you can't let the denominator be 0. Well, e to the x is never 0. This is 0 exactly when cosine is 0. When is cosine equal to 0? So the domain, all the x's except we have to have x unequal to pi over 2, and then, or any integral multiple of pi. So we don't want pi over 2. We don't want pi over 2 plus pi, so 3 pi over 2. We don't want pi over 2 plus 2 pi. We don't want pi over 2 minus pi, so minus pi over 2. And where k is any integer, all of those make cosine equal to 0, and we need to avoid them. And it's a little worse than that. It's not hard to see that we actually have asymptotes there as x approaches these values from the left and from the right. The value of y goes to positive infinity or negative infinity, depending on where you are. It's fairly ugly. In other words, there are an infinite number. This will have, and this is the part I'm doing sort of out of order, an infinite number of vertical asymptotes. That definitely causes problems. It's also, another thing that causes problems is dramatic things happen at the vertical asymptotes that you want to indicate in your graph. On the other hand, the presence of the exponential function, e to the minus x, will make, when x is positive and big, e to the minus x will be close to 0, and it will be trying to make this function close to 0, although dividing by something close to 0 will kind of compete with it and try to make it big. On the other hand, when x is negative and big in absolute value, this part will be huge. So infinitely far out, you'll have asymptotes. And in between those asymptotes, you always get arbitrarily close to the graph and close to the x-axis, and arbitrarily far away from the x-axis. And it's, because of that, it's hard. No window on a calculator or computer is going to show you all of the interesting activity. And nothing I sketch will do it, but we'll know where it happens from using calculus. So let me look at the first and second derivatives and then sketch this, just some part of it, and then leave it. But this is definitely an example where calculators have a lot of problems. So, of course, so do humans. It's not an easy example. So we've got y equals h of x. equals e to the minus x times secant x. And we want to look at where that function is increasing, where it's decreasing. Let's look at y prime. It is the first thing times the derivative of the second. Derivative of secant is secant x tan x. The first thing times the derivative of the second, plus the second thing times the derivative of the first. That gives us minus e to the minus x times secant of x. We can factor out an e to the minus x times secant of x and get e to the minus x times secant x times, we're left with a tan x minus 1. All right. So that's y prime. It is not particularly easy to see where this is positive and where it's negative, but let's do it in some interval at least. So what happens? This function, y prime, can switch signs wherever this is undefined or where it equals 0. Tan x, sine x over cosine of x. So that'll be undefined where cosine is 0. This is undefined where cosine is 0. So the only places, so this is undefined exactly where cosine equals 0. Well, those points weren't in our domain anyway, but we know where they occur. They occur at minus pi over 2, pi over 2. Every time you go up by another pi, 3 pi over 2, or down by another pi, so minus 3 pi over 2. Great. But it could also switch signs every place this is 0. Now, secant is 1 over cosine. It's never 0. This is never 0. Tan x minus 1, that could be 0. Every place that tangent is 1. Where is tangent equal to 1? Well, it happens, if you remember the graph of tangent, it happens at pi over 4. Right? The graph of tangent. Right? Think 45 degrees, pi over 4 radians. Where do you get 1? Right at, so this is pi over 2. So this is the graph of y equals tan x. At pi over 4. You get 1, and that repeats every pi. So where does tan x minus 1 hit 0? Here at pi over 4. And then you add another pi, so that's 5 pi over 4. Actually, let me just draw tick marks. So here's, maybe no, I can't do that. Pi over 4, 5 pi over 4. And this keeps repeating. There's another place right here. All right. So you can see that this gets to be a problem because the sign of this can switch just at all of these places. But you can actually do it. So where is this positive and where is it negative? Like, let's look between minus pi over 2 and pi over 2. So in this range. Between minus pi over 2 and pi over 2, e to the minus x, always positive. At least that part's easy. Secant is 1 over cosine. Cosine is actually positive. Remember, cosine is the x-coordinate on the unit circle. And between minus pi over 2 and pi over 2, that's positive. So positive, positive. The sign of this, so whether this is positive or negative depends on tan x minus 1. Well, tan x is less than 1, so tan x minus 1 is negative here and positive between pi over 4 and pi over 2. Okay. Then what do you have to do? Well, then you look between pi over 2 and 3 pi over 2. There, cosine is negative. So this is negative. This does what it did before. It goes negative, positive. But now it's multiplied by another negative, and you get a positive negative. So this kind of thing keeps happening. And you can verify that the signs do this. The second derivative is equally as bad. The second derivative calculation is nasty. What do you see here? You see that on the interval from minus pi over 2 to pi over 2, just restricting to that interval, between minus pi over 2 and pi over 2, the function decreases until pi over 4 and then increases. So there's a global meaning just on the interval from minus pi over 2 to pi over 2, a global minimum occurring on that interval at pi over 4. And then on the interval from pi over 2 to 3 pi over 2, there's a maximum just on that interval occurring at 5 pi over 4. So it's, the graph of this is very ugly, very complicated. Maybe I won't even try to sketch it, but let you look at it in the book. But the point is, you have an infinite number of local extrema. You have an infinite number of vertical asymptotes. The calculation is not so bad, and you can read it in the book. And you can see, I've sketched it by hand in the book, and I've had a computer do it. It is hard to get a good window where you can see lots of activity. And the calculation is messy, but it is doable, and it's instructive to do it. I suggest you look at this example, but I'm going to leave it here.